air control? Yeah, no problem. Maybe this is good.
Sure.
I changed it.
Oh, okay. I think this. Okay. I think we're settling in.
Whatever you want.
So, welcome back. I guess hopefully everyone has a right amount of coffee and cookies. And it's my pleasure to introduce Daniele Fausti, sorry, who will tell us about temp-mediated thermal control.
Yes. Can you hear me?
I think so.
Yeah. Okay.
Yes, perfect.
So, thanks a lot to the organizer for inviting me. And the purpose of this slide is to say two things. The first one is that I just moved the institution, so we're starting a new group in Erlangen. So if some people is interested, just look us up. The second one is to tell that I flew yesterday night from Europe. So I woke up 3:30, and my body is telling me that I should sleep now. So I hope I can keep up the energy, but if I fail, just try to be understanding. Okay, so I will report our recent results on this, and I'll show you where we come from. I'll just do a fast introduction to see where we come from, and what are the things which, what is the take that we take on the, what is the line that we take on the topics of this conference. Okay. And the argument, of course, is non-equilibrium physics, and it's useless to introduce it to this crowd of people. But essentially, we are interested in non-equilibrium physics on complex systems, and we are interested in two aspects. One aspect, which is the equilibrium response of this object, and that's done a lot in the past, like using non-equilibrium to try to understand the physics of equilibrium, and we try to wrap up something which is known about the language in this review a few years ago. But we are mostly interested in trying to understand non-equilibrium per se, in the sense that we are interested to try to understand how you can use light-matter interaction to obtain new functionalities. Why do we do it on complex systems? We do it on complex systems for the same reason that makes them interesting at equilibrium. And it's you can always think of a complex system as an object which is on the edge of having a big changes of the functionalities. And you can think of using light to obtain functionalities which you are different from the ones that you have in equilibrium. Okay? That's done a lot, but the idea is that we want to use light-matter interaction both as in terms of driving the system as well as in using light-matter hybrids to try to obtain functionality. What I would argue is that in the field, the vast majority of experiments where you have drive in the system and you obtain new functionalities, they are relatively trivial from a thermodynamic point of view, in the sense that light is used just a means to inject energy into the system, while the system, after I injected energy with an impulse of light, evolved towards a thermodynamic power. And the interesting in this community is essentially all those situations where this is different, and we have seen already in Andrea's talk that in some cases light can do something different, and in these cases, for instance, it could trigger the onset of a superconducting state. Superconductivity should appear at low temperature, so what's happening here, like I dump energy into the system, and for some reason, quantum coherent transport sets in, and there's a lot of open problem with that, and we've shown it first almost too long ago on the cuprates, but then there's been a lot of follow-up on the same line, and many people are represented in this crowd, Matteo, and of course Andrea. And this is just one example where the message here is that light can do something more. Okay, and I think it's always useful to stress these two aspects about equilibrium for non-equilibrium for equilibrium or non-equilibrium per se. In the sense that when you do non-equilibrium for equilibrium, you're interested in a weak perturbation. You can still rely to some extent on a fluctuation dissipation relations or to ideas of expanding order parameters. So you do have some tools, but of course when you go out of equilibrium, you need to think about the problem in a much more complex way. And I will try to show you where we are with it. So we are interested in general in these situations in which light can do something that it doesn't do at equilibrium. And one example, and I won't give much detail here, you find the detail published it's a situation in which we did an experiment very similar to the ones that Andrea has nicely introduced in the morning, in the sense that we wanted to demonstrate that by resonantly driving some vibrational mode, we could gate some electronic transition. So in some sense going against the Born dynamics. To do this, we choose the system that is one of the family of the cuprates, but is peculiar because it has the absorption which is characterized by DD on-site transition, and this DD on-site transition should be forbidden by selection rule because the system has inversion symmetry, but they are actually visible in the optical absorption. And people describe this situation as phonon-assisted transition. I spare you the model, but essentially every time an electron is absorbed, there is a phonon that participates into this process and breaks the symmetry. So whenever this was for us the ideal platform, because whenever I can drive a vibrational mode, very similar to what, as I said, Andrea showed before, I can try to ask myself, how does this driven vibrational mode modify the electronic absorptions? And the results, which I summarized just in one slide, it's essentially that it's one of the situations which is interesting, because if you look at the optical absorption at equilibrium, when I increase the temperature, I always increase the absorption, in the sense that this is, if I think that this absorption is mediated by thermal disorder, the more I increase the vibrational disorder, the more I will absorb. And that's visible in linear absorption. On the other hand, out of equilibrium, we saw that we revealed a region where I increase the transparency of the system. And increasing the transparency allow me the formally non-correct analog, but essentially it tells me that I can, by putting energy into the system, I can produce a situation in the material which is analog to cooling the fluctuations of the material. And the fact that I can go to a transparency which is larger than the transparency I have at zero temperature, it means that I can cool. I can say, if I want to say something fancy, I would say I cool it beyond the vacuum fluctuations of the system, but to say it honestly, we do something else. Okay, we drive the ions and we do something else. But the general message of these slides is that whenever I want to do something which goes against thermodynamics, there is a quantity which I think it's crucial, and it came out in different talks, and it's the quantity which is the fluctuations in the system. So rather than driving the system, I should try to dynamically control the fluctuations. And we've seen, for instance, also in the cosmonic thing that was mentioned in the morning, that the interesting effects comes from the fact that I can induce a non-trivial fluctuation structure, time-dependent fluctuation structure. So our big activities was it has been along two lines, and the first line is we developed a lot of tools over the last 8 years to try to measure fluctuations in matter. And I'll just show, in fact, I'll take 5 minutes to show where we are on that, and then I will go on the main results that I want to report, which is our new directions of research to try to control fluctuations, and of course the activity here on cavity electrodynamics, it's part of this. So our idea was to try to, if I want to dynamically measure the fluctuations of some relevant degrees of freedom in matter, I should try to define an observable which allow me to measure these fluctuations. And of course the observable depends on the specifics of the problem, but the general philosophy that we have tried to follow over the years is the following. So whenever I do a dynamical experiment, I usually focus on studying the property of the material, and light is used on one hand to perturb the material, and on the other hand to measure the material response. This is just an obvious pump and probe experiment for this graph. But what I need to stress here is that this is like this if I focus on the material properties. If I am asking myself, what do I measure of the object, or the light pulse which I use to interrogate the system, I'm actually measuring a relatively trivial quantity. So I have a certain number of photons coming in, certain number of photons coming out. I make the average, and I can tell you what is the response of the system on average. On the other hand, if you look at the problem from this point of view, it comes clear immediately that this carries only part of the information that I can have, and I can ask myself, for instance, do I have information in the fluctuations of the photon number? For instance, do the fluctuations of the photon number carry a spectroscopic information which I could use to understand what are the fluctuations in the network? And it's a set of work, so I won't give details here, but in certain very limited settings or certain settings where we understand light-matter interaction fairly well, I would say that we are at a good level in that, in the sense that we can find a situation in which some relevant material fluctuation is mapped directly onto some measurable optical fluctuations, and we have worked a lot on this as well. The other aspect which is interesting is the fact that if I follow this logic, I don't need to go to the quantum limit, but I would have information which I can retrieve also in the classical limit. And here I just want to have 3 slides to show this how do we use classical fluctuations and what kind of information which may be relevant in terms of spectroscopy we can carve out. So this is one of the main messages of my seminar. One of the 2 messages of my seminar is that in general, when I do non-equilibrium physics, I want to measure the nonlinear response, and the nonlinear response is usually small, and therefore I need a very stable laser source. But this is true only if I measure the average. And the argument that we have tried to push again over the year is that if I measure something else, for instance, I measure what are the spectral correlations between in repeated measurement on equally prepared state, the noise can become the source of information. So the idea here is that we want to repeat measurements on equally prepared state, and rather than making the average, we ask ourselves, how does the probability of having a photon in one spectral component correlates with the probability of having a photon in another spectral component? And that, to some extent, it carries an information that is not there if I just measure the average, and I try to convince you that this is actually possible. So these are the kind of measurement that we do, and here it's just numerical simulation, just to see what this mathematical object tells us. I introduce intensity fluctuations in repeated measurement of my light pulse, and I ask myself, how does the fluctuation in one frequency component correlate with fluctuations in other frequency component? And I get, in a plot frequency, I have this blob which actually saturates at 1. And how do I understand it? I understand it because if for a given realization, this spectral component is more intense than the average, this other spectral component is more intense than the average, and that's true for all spectral components. On the other hand, if I have, for instance, frequency fluctuations, if I have the system where I have a frequency jitter in my laser, I do have correlators which are a little bit more complicated, but are also relatively easy to understand, because if in one realization, spectral component on the right are above the average, spectral component on the left will be below the average, therefore I have negative correlations between spectral components which are not inside the pulses. And what is the most interesting situation is a situation in which I have frequency uncorrelated fluctuations. So fluctuations, I lost it, yeah, I should be sleeping. Fluctuations which are actually local in frequency, where essentially the fluctuation in one given spectral component correlates only with itself. Why is this interesting? Well, it's interesting because, as I said, the target for us is the non-equilibrium response, which is the nonlinear process in the system. And if you think about the nonlinear process, for instance, as impulse stimulated Raman, which destroy a photon in one frequency component and creates a photon in another frequency component, which is related to the first one by the frequency of the boson, which mediated the scattering process, then I can think that if I start from frequency uncorrelated fluctuation and I allow this scattering process to happen, I will introduce correlations between different spectral components. Of course, this will, because if a photon disappears in one frequency component, it has to appear in another frequency component, which is big omega apart. This is like what we did in the past, and essentially the idea is that we develop means to produce very frequency uncorrelated pulses. This is like a measurement of intensity fluctuations in my laser system after I deliberately made it bad. And if I look at the correlation is essentially local in frequency. I take the same set of pulses, I make them interact with the sample, and the interaction with the sample may introduce some correlations. Of course, if I look at them pulse by pulse, very little I can learn here because it's as ugly as before, but if I actually look at the correlations, I see correlations at very specific frequencies, which are the frequency of the phonon which mediated the scattering process. Okay, so the idea is that I try to encode information in the noise and try to extract information from the noise so that I can sort of cheat around in determination.
Can I ask a question? Why don't you get a narrowband laser?
Because if you get a narrowband laser, you lose time resolution. Instead here, I said you cheat around in determination in the sense that your frequency resolution is given by the width of the noise, while your time resolution is given by the inverse of the width of the pulse. So that's a little bit like femtosecond Raman spectrum. So this can be done in many forms. I just go fast here because I want to go to the cavity, but essentially you can also shape partly your light pulse, and you can see that you can you measure even weakly scattering phonons, and you measure them with a relatively high frequency and time. As I said, the good thing of this setting is that now I can go to a pump and probe setting, so I can perturb my sample, so prepare an excitation in the sample, and I can look at the time evolution. So I will measure the time response of the sample, which has a very high frequency resolution, because the resolution in frequency is given by the width of the noise, while on average a very high resolution in time. And what is interesting for this community, apart of the technique which I highlight here, is that I just want to flesh out what are the kind of things that, in my opinion, could become very, very interesting, and that's the following. We apply this technique, and these are like the first unpublished results I show, that we are trying to consolidate them for months now. It's a very hard experiment for us because it requires a lot of data acquisition. But essentially, in cuprates, you are sensitive to electronic Raman scattering from the superconducting level, and that's well known in literature that if you select different configuration, essentially you can be sensitive to electronic Raman scattering, which is associated to nodal or anti-nodal excitations. So that's one almost 15 years old reference. But essentially, what I want to be very procedural here. So there is a broad electronic scattering which is associated to the onset of a superconducting state. And it took us a while to get convinced that what we are doing makes sense, but we started first on simple systems. And the idea is that we measure as a function of pump and probe delay. Now we can perturb the sample and quench the superconducting state, and we try to measure the correlations as a function of time. And I can, now that I know how to analyze after I spent 3 years on simple systems where the phonons are very narrow, so I know that the only relevant quantity is the distance from the diagonal. I can actually confidently measure this quantity, and I can compare it with the Raman scattering, and essentially I realize that in the superconducting state of the cuprate, if I interrogate the system with these very wobbly pulses, I introduce spectral correlations who are in frequency very similar to the spectral correlation I do by Raman spectroscopy in the superconducting state. What could turn out to be a very interesting observation is the following. That now I can measure how this frequency how this Raman scattering evolves in time. So I can measure information which tells me after I perturb the superconducting state, how does the spectrum of electronic excitation evolve in time. And I see that I can measure the relaxation time of this scattering feature. But what's more interesting, and here it's not a result yet, but I would like to present it as a discussion argument, to which I hope I managed to go at the end, is that if I go outside of the superconducting state, this scattering feature is completely gone. If I go inside of the superconducting state, it appears. So it is somewhat associated to the superconducting state. But if I go above the critical temperature, I do see that I have a remaining scattering feature, which is similar to the scattering feature I have in the superconducting state. And this is not true for equilibrium Raman spectroscopy. If I do a continuous Raman spectroscopy, this electronic Raman scattering disappears at the critical temperature. That's why historically it was connected to the onset of a superconducting state. Okay. What would be very interesting, we're trying to work on two sides. On one side, we're trying to consolidate this data, and on the other side, we're actually trying to look at how should we reason about it. But a very compelling reasoning direction is the fact that I see a scattering feature in the superconducting state may be related to the fact that with this technique, I take snapshots of the interaction of my lasers, because the interaction time of my laser with the superconducting states are very, very short. So essentially, we're trying to reason of whether this could be interpreted as yet another evidence of the presence of superconducting fluctuations above the critical temperature. But it's work in progress, so we just want to use it as an argument where we will go at the end. Okay. So the main title of my seminar was not how to measure fluctuation. I just wanted to highlight that there's a lot of work that we have done over the years. But the most recent direction that we have taken is an attempt to try to control fluctuations, as we have learned from non-equilibrium that fluctuations are the key aspect to control complex materials. So how do we do it? And we resort to cavity electrodynamics, as other people in the crowd did a lot on that. So can we use cavity electrodynamics? Yeah.
The biggest part. So these measurements are high power measurements.
Yes.
So shouldn't be overwhelmed by Gaussian, and if it's Gaussian, then everything can be understood by just 2-point products.
Okay, that's a question which will require a very long answer. So what we have done, we have introduced Gaussian noise, and we have seen that essentially the correlations functions that we get out are also Gaussian, in the sense that I can recast all the higher order momentum to the second and the third order. Yes. But that doesn't limit it, in the sense that you can think of introducing heavy tail distributions. We haven't done it, but it's just a demonstration of the principle. Yes.
Again, just following. So you said that it becomes Gaussian. Is that experimental fact, or is
Yes.
that expectation? Because you're only quantifying the second moment. Do you know that the fourth moment is described by the second moment?
We have looked a lot in trying to understand whether we can generalize this to higher order momenta, and we have tried actually Filippo Beren is on the crowd, so he did a lot on that. We've tried to see whether we can have additional information in 3 intensity correlation, 4 intensity correlation, because we have the data. But essentially, you can retrieve very interesting information, but to the best of our understanding now, we could recast the higher order correlation function as a function of the lowest order correlation function. This is the level of understanding that we have now. But it's a direction where we are going, where we have gone. I don't have anything interesting to say about it yet. So that's yes. So can we use cavity to enhance fluctuations in some specific frequency? Okay. So the idea is I shouldn't introduce it to this community, but essentially that if you can force a continuous exchange of photons between matter and cavity photon, you can think of a controlling material functionality with cavity. There's a lot of discussion on whether this is even possible and to what extent this is possible. So there's on one hand, a mounting experimental evidence that something can happen, and yet at the same time there's like many theoretical questions of whether this is possible at all. So it's a very vivid place to be at the moment. So we have developed our own settings to try to test this. So essentially we have like samples in fabric rock cavities. They are all cryogenic, so we can control cold mirrors. And the idea is that once you tune your cavity resonance to the material transition, you could think of forcing this exchange and increase the interaction, just in terms of, for describing it in terms of naive Rabi physics. So that we choose a system to demonstrate that this is possible. We choose a system where we have a sharp phonon resonance, and we tuned it in resonance with a cavity, which we could tune across this phononic resonance, and we observe that we do have a large collective coupling, in the sense that we have a Rabi splitting which is larger than the phonon line width and than the cavity line width. Okay, and we could. I think that the merit of our approach is that now we can actually fully tune the cavity, and we can see the avoided crossing, and just to explore essentially the coupling as a function of the frequency of the cavity. The setting works, and the first interesting problem that we study is we took a charge density wave material, tantalum disulfide, known to the community as in many different aspects. I haven't seen it in this conference, but it will pop up soon, I'm pretty sure. That we choose an observable. For us, the observable was terahertz spectroscopy, and we could actually see that we do have a weakness of this metal insulator transition, in the sense that the terahertz transmitted in the metallic phase is essentially featureless, while the terahertz transmitted in the dielectric phase, there's very sharp resonances. You can look at the resonances directly, and we will use this just as plain data. We will not do anything on the data, but of course, you can actually also extract the optical conductivity, and you see that the optical conductivity has three very sharp phonon resonances in the dielectric phase, but as soon as you increase the temperature and you go into the metallic phase, the free charges completely screen the phonon modes, and the system becomes metallic. It's seen in continuous resistivity, and it's seen also in AC conductivity in terms of a Drude peak at low frequency. So we have an observable. We can measure this phase transition, and we fix our cavity so that we can measure the temperature of the support of the sample, and we can actually cool down the system or heat it up, and we see a transition from a dielectric response which has three sharp phonon resonances, and it actually, I can see like I can map the hysteresis as a function of the temperature of the support of my sample, and basically I can see a transition from an insulating state where I have sharp phonon modes to a metallic state where the transmission is featureless, associated to the response of the material. Okay, and now I will start first from unpublished data, and then I will go to published data. So I will try to discuss what's the difference between coupling the cavity to the different objects in the problem. And I will start by coupling the cavity to the phonon modes. I will go to high frequency cavity, the highest frequency that we can reach. Highest frequency means that the cavity, the smallest cavity that we can do, it's the thickness of the sample. Okay, and I can tune my cavity across this phonon mode, and what I expect is that if I take a sharp cavity resonance and I try to couple it with three phonon modes, I start with 4 states, and I should get out with 4 polaronic bands. Nothing really peculiar happened. I just couple this object to these phonon modes, and it turns out that I can study the coupling of the cavity to these phonon modes, and I can observe the polaritonic state dispersing and the two states in the middle which are not dispersive. That can sound surprising, but it's nothing particularly interesting, so we can rationalize it at the level of theory that experimentalists can do. So we can take three resonances, three phonon resonances, and we couple them to a cavity, a single cavity mode. And essentially you see there is the interesting aspect is the fact is not, in my opinion, in the polaritonic states which are dispersive, because these behave like if I had a single phonon mode coupled to the cavity. So I switch from a cavity state to a light state in the system. But what's interesting, I believe, is the region in between, in the sense that there is if I try to look at how do I rationalize in the Davis-Cumming Hamiltonian the states which are in between, I see that in the middle of the cavity I build states which are composed not only by light and matter, but by multiple excitations in matter. So I expect that the nonlinearity in the system would be very relevant, and we are trying to refine the model to try to understand whether we can retrieve in this setting, we can retrieve in this setting some nonlinear phonon.
Sorry, what's on the vertical axis?
The vertical axis is the component of the modulus of the component of the wave function. So essentially, this is telling me for the four states I observe how is the wave function composed, and for the lower polariton and upper polariton, I switch from being mostly cavity mode to mostly one phonon mode where the cavity goes across, and the same for the upper polariton. But the two states in between, they are composed by two different phonon modes and the cavity mode. So I can expect that the nonlinearity here could be relevant in the sense that I mix different phonon modes. Okay, we can, I go fast as I have 5 minutes, so we can study this cavity resonance in the dielectric state or in the full metallic state. And you see that in the metallic state I have only one single cavity mode, which is, there's no specific resonance of the phononic state. But what is interesting is in the proximity of the phase transition, because if I, let me skip this, if I try to study just above, very much above the critical temperature where the system is in a well-developed metallic state, I do observe a single cavity mode, and if I plot the quality factor of the cavity mode, the quality factor simply increase, which is due to the frequency of the denominators, essentially. Nothing particularly interesting here, just I increase the frequency. And therefore, I increase the quality factor of my cavity, having the same losses in the cavity. But what's interesting is what happens just above TC, because if I go just above TC, so in the situation where I have mostly the Drude response, so I don't see in linear response the phonon, I see that the quality factor of my cavity is a non-monotonic function. And if I go and look at which frequency I have this non-monotonic function, I find the frequency of the phonon mode of the symmetry broken phase. So as if in some sense the phonons are no longer visible in linear response, but they still participate in the dissipations. So the cavity is mostly coupled to free electrons, but there is a scattering possibility to the phonon mode to group.
Second order or first order?
First order transition. And so in some sense the cavity it allows me to measure the dissipation of phonon modes, which I don't see.
So that's inside the hysteresis cycle that you see this?
No, outside the hysteresis cycle, above, yes. That's the peculiarity. The other interesting region is if I go on the Drude response, and I just want to, I go fast flashing out the results here. I see that the Drude response is visible in the cavity mode. I have one single cavity mode, which becomes broader when I'm in the metallic phase, meaning that the electrons participate in the dissipations of my light matter system. But what's most interesting is if I try to go in a situation where I see both the fundamental mode of the cavity and the second mode of the cavity, I realized that the fundamental mode of the cavity is very sensitive to the presence of the metallic or insulating state, while the second mode of the cavity essentially ignores the fact that the layer I have in the middle is metallic or insulated. And how do I understand this? I understand this because the second mode of the cavity has a node in the middle, so essentially it ignores if the object in the middle is a metal or an insulator because it has a node anyway on the shape of the node. So that proves in some sense that I'm sensitive to the mode structure.
So it means that it doesn't really couple essentially, or is that what you're saying, or not?
It doesn't really couple because the mode has a node. Yes. So I don't see if the system is metallic or insulated because I have a node anyway. So the field is defined. But we used it to convince ourselves that we see the modes of the cavity.
I guess you also have higher ones that you don't.
But then in this case, if you are in that regime, they fall in the phonon bands. So we don't see it. So the published work you can find it in the published paper. So I can go very fast here. So essentially, we realized that if we place the sample in a very large cavity, we can change the apparent phase transition temperature. I say apparent phase transition temperature in the sense that this is the phase transition of the temperature of the support of the sample. And it's a real shift in the sense that it's a static shift that I can observe. And it is controlled by the mirror in the sense that if I plot the hysteresis as a function of the mirror angle, I can misalign the mirrors and I can go back to the hysteresis. I have almost to the hysteresis I have in free space, and I can even fix the temperature of the support, and just by changing the mirror, I switch from metallic to insulator, and I can do the opposite in different conditions. So I essentially can control whether the system is, I go very fast because the chair is getting nervous, I essentially can control, but this is all published, so you find it in the publication. So I essentially control control whether the system is metallic or insulator just by controlling the mirrors. How do we discuss this problem? I think it's important to be clear here. There's like two ways you can think of, two directions in which you can try to understand the physics of this problem. And in one sense, you can think that the cavity modifies the physics of the sample, so the coupling to the cavity modifies the physics of the sample. Or you can think that the cavity changes how the sample sees the environment. Because in some sense, when my sample is in between the cavity, I filter the radiation load that it receives from the black body around. Okay. So we worked out two interpretation frameworks, so to say, in a sense that you can think that the cavity changes the free energy of the two phases. So you can think that the cavity couples selectively to one phase with respect to the other, and therefore just by renormalizing the free energy of one phase with respect to the other, it actually shifts the phase transition temperature that I measure. Or you can think in the alternative framework, which in my opinion it's more interesting. You can think at the system as if it is an open quantum system in which the sample is actually coupled to the object which pulls it, but it's also radiatively coupled to a photon buff. And the coupling to the photon buff is shaped by the cavity. And you can, therefore, with shaping the geometry of this object, I can shape how much the black body around my sample hits the sample. So in some sense, I change essentially the emissivity of the sample just by shaping the black body around. And we think that the second mechanism, so the status for us is that we are sure that the second mechanism is at play. We don't know whether the first mechanism is also at play. Okay. So I think that it is important to because leaving the system open, so leaving the system open to exchange of energy with the environment, go around the problem of phase space, where essentially a single mode cavity would give negligible thermodynamics changes in the thermodynamic limit. So these are the conclusions, and I just want to flesh a little bit what I think is very interesting and where we want to go. So one platform where we want to apply this concept is the Cook rates, because if it's actually true that we do have unstable superconducting fluctuations above the critical temperature, what the cavity could do, and there is a dipolar coupling between the gap and the system, what the cavity could do, the cavity could mediate long-range interactions, and therefore could, in some sense, in some hypothesis, working hypothesis, it could actually increase the coherence of the states, and therefore eventually increase the critical temperature. But what I think to my taste, this problem, it's actually a very general problem in which if we can engineer the coupling of the light to the modes in the system, we can actually think of addressing a completely new thermodynamics in which I use the cavity to inject fluctuations in the system in a specific spectral bandwidth. And if the system in the cavity has a complex thermodynamics by itself, I can actually think of even sustaining non-thermal stationary states, and where eventually I could try to trace the dissipations in the system, and they can sustain situations in which I have non-thermal states, even at the stationary level. And with this, I need to thank the people, otherwise I will be blamed. So the first part of the fluctuations has been done is now led by Anja and Enrico in my group, and many contributions from former member. One is here in the crowd, is now local, Filippo. And the theory has been supported by the group of Sean Mutterman, different people. And the cavity instead has been led by Giacomo Nisciala. And the theory has been mostly done by Francesca and Martin Einstein. And of course, thank also the funding institutions.
I think we'll have time for one quick question while the next speaker sets up, and I think he raised them.
Thank you for this very interesting talk. So I would like to compare your last results to similar discussions that have been going on with the chemistry community. And we worked on a very similar problem as yours, and we concluded that the only way we could explain it is also similar, like a black body effect. But then the question still arises of why conductive heat transfer is not overriding the radiative heat transfer that you are invoking in your explanation.
That's the core of the problem.
Because that to me is also very mysterious. Why would it be the case that the radiative heat transfer is dominating over the conductive one? And normally that's a very strange situation where that would really happen, as far as I understand from talking to engineers about this.
Yes. Let's say I can give you a qualitative answer, in the sense that I think that the radiative transfer can be very strong when I have collective states in the system. Like for instance, in this case of charge density wave system with high disorder, the oscillator strength of these states could be very, very strong, and eventually I leave energy only in the electrons. But I think the real answer is that this is like open to question. Because I can think of situation in which if I have a quantum collective state in the material which has a lot of oscillator strength, I can think that the cavity perturbs the system so that eventually it can reach non-thermal stationary states. I think this is a perspective that in the vast majority of the simple materials wouldn't be relevant, but in complex materials, which they are very susceptible to anything we do to them, it may be very relevant.
I mean, any ferroelectric has an enormous oscillator strength for the soft mode, so that means any ferroelectric you put in there should, right?
Yeah. So I think that the key answer is that it's not an answer in the sense that, but if you look at the phase diagrams of cuprates, manganites, and all the complex material, you just tune the pressure of like a few pascals, and you go from insulator to metal. You just tune the temperature of 5 degrees, and you change completely the physical properties. So the coupling, shaping the coupling to the black body around may be very relevant. That's a general statement.
Great.